Okay, so yesterday, this is sort of right where we left off, getting ready to go over power. We've talked about uh, different types of work. Work is just a transfer of energy from uh, one thing to another. Or, no, I should say energy is a transfer of work. And work was just saying, I'm going to force something over a distance. Now, these two things, energy and power, they get thrown around in the same sort of domain a lot of the time, but they're not exactly the same thing. Whereas energy was how much work you can do, it's just sort of a value. Um, it takes so much work to push this box up this hill, or this crane can only uh, lift this thing up so much, so it has so much energy it can offer. Power is something that says how much time will it take to do something like this? How much time will it take to transfer energy from one thing to another? So we have this, let's start where we kind of were yesterday, where we have just, what if we just have a sliver of work? It's just dw. So imagine I was to push this through an integral eventually. I'm not going to do that right now. I'm just going to say this is equal to kind of a result we found yesterday. Is the force times the force vector times a displacement vector. So this was the dl from yesterday. Why is it dl and not just l? Well, it's me sort of, I'm sort of mashing a bunch of steps together. This would go through an integral, and out would come this power equation I'm going to write down. But I'm going to say that this is just saying a little slice of work is just a force times a little slice of displacement. This is equal to a little displacement. If we sort of time this thing, a little displacement with a little slice of time, that's just force times, that's basically the velocity of this thing times that little slice of time. So how quick was it moving? The force moving this object from one thing to another. So we have that's displacement and it's easily, we should see how it can, be turned into a speed if we just, instead of measuring the distance it covers, if we measure the time it's taking to do that. So we have power is basically just the rate of change of work. So a little slice of work over a little slice of time. So an amount of work over time. You could also say this is equal to force of whatever force I'm applying to an object times the velocity the object is moving. Okay, so we have this equation for power. Let me really quick give the units for power. Power is measured in watts, and a watt is, if I just look at this fraction right here, that's basically just a joule, 1 joule. of energy over 1 second is 1 watt. Okay. Let's do a little power example and then we'll basically be done with this chapter 6. Ooh, just a little too big. Okay. All right, so a small motorized lift raises a load of bricks weighing 500 newtons. By the way, on a typical scale, like you have in your bathroom, it's measured in pounds. Pounds is just similar to newtons. It's just measuring a force. So when we say pounds, it's just a force downward. I believe it's like the imperial way of measuring force. There are scales you could buy that just give you your weight in newtons. That's sort of a little aside. But for this problem, lift raises a bricks weighing 500 newtons to a height of 10 meters in 20 seconds. Assuming a constant speed, the lift itself weighs 300 newtons. All right. So let's do a little diagram. I don't got to draw the whole thing, but I'll just say we have our, lift and our set of bricks. I'm combining into this square. And the whole thing is being forced upward by a motor. As always, we have gravity trying to force it downward. And what do we have here? We have the problem is saying that it is raising it up. It's lifting it from a lower height to a higher height in some amount of time. So that means there is a force upward caused by the motor, and it is moving upward. So from yesterday, we talked about dot products and the vectors not necessarily lining up. This one, we could see that there is no difference in these two vectors right here. So the angle phi, the angle difference is 0. And I'll use that in just a minute. So we have our power equation we could write down. Power is force times velocity. These are both vectors. They're both, the direction is important. And since I already know it's being forced in a direction and it's moving in that same exact direction, I can use this form of doing the product of these two vectors. I could say that's just the magnitude of each. So force without the vector sign times velocity times cosine of phi. That's where you might see this will come in handy. Because if I say that cosine of phi is, and phi is 0, cosine of 0, that's just 1. So we have this whole thing. Power is just force times velocity in this case. The magnitudes of each. Pretty simple calculation now. The force is, the force of, I should have a little subscript right here. This is the force of gravity right here, or how much does how much mass, or here I should put it. We have this weight of 500 newtons. We have this weight of 300 newtons. That is how much this motor is lifting, if that makes sense. So it is lifting this amount, a specific height. And it lifts it 10 meters in 20 seconds. That is distance over time. That is velocity. So we have 4.0 times 10 to the second watts of power that this motor on this little lift can output, at least from what we're seeing from this example. Okay, the last thing for this chapter that I want to cover, and I don't know if I will have anything on the homework with this, but I will just write it down for completeness. We have the work kinetic energy theorem for curved paths. This is the same exact sort of arrangement as a straight path, except now we need to factor in how force may change as something changes its direction. And actually, I'm not even going to get really into it. We have the same starting point. Work is basically just the change in kinetic energy of an object. And if an object is changing kinetic energy in two-dimensional space, we just need to make sure to include we include the limits on where it's starting, where it's stopping, integrate over. It would probably be like a function that's given to us for a problem like this. So I'm just gonna just say if we have something like this, it would be force times sort of this winding path. Now, you can think of this as maybe two-dimensional. And delta K, that's just final minus initial also. All right, so that's handy to have. I don't know if I would have something like this on a quiz, since I have to put so much material in a quiz in the first place. In a regular semester, I might keep this around a bit more. This is for curved paths. And that is pretty much what I want to cover in chapter 6. Chapter 7 moves into conservation of energy. We've talked about work this previous chapter. Work is a force over a distance. That is some energy. How does that energy move from one object to another? in a a previous day's lecture, I said that work can be done on an object or by an object, and it can be positive or negative. How does energy really flow from one thing to another? That's what we're going to maybe examine in this next chapter: conservation of energy. So for conservation of energy, imagine that we have a system that's, well, actually, let me write down this, my own sort of take on the definition, and then I'll talk about it in a bit. So conservation of energy says that the total energy of a system and its surroundings the total energy of a system and its surroundings does not change. And I'll say that energy is neither created nor destroyed. It is only transferred between systems. We run out of space. Only transferred between systems. Okay, I'll clean that up in a bit. Class is over. So there is, I can give some of my own energy to move a box on the ground, or a crane can give some of its own energy to lift, whatever shipment it's doing. This is me applying a force, and something that we're calling energy now is changing. Well, how much energy is possible to give or to receive? Something that we can keep in mind is we could always sort of zoom in on the immediate area of like the problem at hand, and we can say that everything within this sphere of the problem, all of the energy remains here in this system. Conservation of energy says that there is no change in the total amount of energy in this sort of bubble that I'm looking at. The energy only just transfers from one thing to another. So me heating up dinner in an oven, I look at how hot my food is when I pull it out. Where did this heat come from? Well, the oven had to produce the heat and transferred it into the food. There isn't sort of this creation of energy out of nowhere. Well, where did the oven take it from? Well, the oven took it from the the coils running back and forth inside, and that took it from the electrical grid of the city. Where'd that come from? Came from hydroelectric dam, a couple cities over, and that came from hydroelectric potential. That is just falling water spinning some gears. So it's this continuous transfer of energy from one thing to another, and energy is neither destroyed nor created out of nowhere. It's always just transferred. It's whatever sphere you want to zoom in on, you can always say the total amount is the same. So we have this kinetic energy we were talking about earlier that deals with movement. Kinetic energy is, we've already covered pretty thoroughly now. Kinetic energy is pretty much how you can describe an object in motion. A description of how much work is being done in order to move an object. So this is like measuring the object's mass and its velocity, seeing its energy that way. There is a different type of energy called potential energy. Potential energy is quite what it sounds like. It's how much energy does this object potentially have sort of stored inside of it. And the reason it's called this is it's a description on how much work is being done to maintain a current configuration. And I phrased that pretty vague, so we'll cover a couple of these types of energy. So to maintain a current configuration. What does that mean? Well, there's two types that we're going to cover, at least today. There is gravitational potential energy. The one we'll probably deal with the most in this class. I'll just bring up the second one also. It's gravitational potential energy. There's also elastic potential energy. I think there's, several other types that we're not going to go into. Like, I think there's chemical potential energy. If you were to go into physics 4B, there's thermal energy or thermal potential energy. So these two are what we'll cover today, and you'll most likely see around this class. It's gravitational potential energy. Maintaining a current configuration, what does that mean for gravitational potential energy? So I'll phrase it like this. How an object with mass is located with respect to nearby larger objects of mass. Okay. So going through the schedule, I had to cut gravity completely from our sort of to-do list for the summer session. But in that, I would have gone over a bit more about gravity, and that every single object with mass has their own gravitational potential energy that it exerts on other objects. If we were in blank space, so not even stars visible in the sky, and you're somehow still able to breathe and live, if I were to hold out, say, like an apple or something, a ball, a distance from me, I would be something with mass. This apple is something with mass. And both objects with mass have their own gravitational potential energy, but they exert this sort of pull on one another. So if we were out here in a void, I could like place an apple or whatever some distance away, and the apple would sort of be attracted just by being in the presence of another object with mass. Same thing, uh, it does happen here on Earth. Like I am gravitationally attracted to stuff on my desk. You guys are gravitationally attracted to stuff in your room. It's just that the largest thing with mass that we're all near is the Earth, and the Earth is so much larger than my charger I have on my desk, that I don't experience this gravitational potential energy from this tiny thing of mass. For elastic potential energy, that is, let's work through that definition. We'll say this is, think of like springs, elastic bands, things that stretch. How much energy it takes to maintain a current position for a spring. So this doesn't necessarily always have to work, this doesn't work only for springs, is what I'm trying to say. It's how much, I can compress a spring, how much elastic potential energy is there. If I, I'm squeezing it and I'm just holding it still, it's not moving. There's no kinetic energy, but I'm still maintaining this configuration. So there is some elastic potential energy stored in the spring as I compress it or as I'm stretching it. Even though there's no motion at all in the system, it still has some potential energy. A good way to think about it is like the potential energy can all of a sudden be transferred into kinetic energy at a given moment. In fact, we'll go into, as these energies transfer from one form into another, there are what are called conservative and non-conservative forces. Just barely too much. Okay. So for a conservative force, if the total work done on an object only depends on the final and initial position, and let me underline, and not the path taken, this is called a conservative force. So at the top of this page, I've written that all of the energy stays in a system. Well, if I move, my object around, here, there, or say I move an object to the right, positive amount of energy, then I move it to the left and stop at the same spot. That was a negative amount of work. If the path that I take does not matter, only the final and initial position, this is called a conservative force. So it's like no extra energy was needed. All of the energy that I put in, I got out. The energy was conserved. I'll do a little diagram to maybe show this at the bottom of the page. So we have conservative forces and non-conservative forces. If the total work done on an object does depend on the path taken, this is a non-conservative force. So let me bring up a picture that will hopefully demonstrate this. So I'll just bring both of them up. We have two exact situations that I'm going to say that's one of them is a conservative path, one is a non-conservative path. Okay, so it's the same exact sort of amount of force. I'm just applying something slightly different on each of them. So we'll say for this conservative path, it's saying that the path does not matter. Well, let me sort of describe this picture. Let's say I push a box to the right and it's on some sort of loading area and it's lifted up by a crane to position 3, and then the crane brings it back over. It decided it didn't want it anymore, and it brings it over. That is sort of frictionless, and then it lowers it down to its starting point. So where does it start and where does it stop? So it starts right here and it stops right here. So just from that sort of small observation, if I look at these final position and initial position, and the energy amount is the same, that's a conservative force. So let me maybe clarify with this. If I put in some positive work in the X direction, and then the crane lifts it up, positive work in the Y direction, and then it brings it back, negative work in the X direction, then it lowers it down, negative work in the Y direction. You can see that all of these terms cancel one another. I should also clarify, this is a frictionless surface. So this is one of those, physics problem, completely frictionless surfaces. So I'll say that the path does not matter. returns with the same amount of energy that it starts with. Okay. Let's look at this non-conservative example here. Well, a way for me to show non-conservative forces is let's do the same thing, except now this floor is, I don't know, rubber. It has some friction now. Okay, so we're pushing the box along this surface, and it's still a positive amount of work in the x direction. But remember, friction always opposes movement, and so it'll be minus some friction amount. That's a force that's opposing this motion. And then the box lifts it up, or sorry, the crane lifts it up some amount, and it brings it back. We'll assume this whole process is still frictionless, so it moves around this other part of this cycle. And there's no friction up here on the top as it moves back. And like this, and we see all of the terms cancel, except there's this difference of force that was required. And that was purely on the path that I took in moving this thing. So I'll say the path does matter. So whenever the path does matter, whatever sort of things going on in your system, you have to see what are the non-conservative forces at play here. In this case, this one that I circled, that's friction. Friction is a non-conservative force because it always opposes movement. I'll just sort of like this. For this one over here, it returns with same energy. For this one right here, I'll say it returns having lost some energy. Okay. And it's not necessarily that, let me clarify. It's not that the energy just fizzles out into space. It's friction. So it's me going over this surface. It's all of these jagged bumps bumping on top of each other. That's turned into sound. It's turned into heat on the surface of both of the objects. That's that kinetic energy that I was supplying is turned into sound energy. It's turned into thermal energy of friction. So it's not like it just vaporizes and doesn't do anything. It's sort of spread out. But still, if I were to, I'm gonna make a mess with this picture. If I were to draw a sort of a quarantine sphere around this picture, I could say all of the energy in here stays the same. It's just some of this energy gets transferred into warming the floor right here. Hopefully that's clarifies on where energy goes, transfer of energy, conservative, non-conservative forces. Let's do some examples. We'll bring up potential energy and elastic. First up is potential energy. that. Okay, let me, yeah, so we have potential energy. We want to know how much, an object's position next to another position in another object with mass. How is that related to the force required for anything? Well, we first are going to define potential energy as U. That's just capital U. In other books or maybe some videos, you'll see potential energy is just capital PE. That is also correct. Our book just says this one is U. That is, it's either U or PE. It's not like they just chose a random variable. So for this potential energy function, we're first assuming that it's conservative force, so we don't have to deal with where is this leak of energy happening. We're just going to assume it's conservative, and we're going to say that the change of potential energy is, well, that's just basically 2 minus 1. It's final potential energy minus its initial. And that's just what happens to the force required as you move this object near this other object, or with its configuration. I'm sorry, there's a minus sign. So this is potential energy in general, which tells us that if there's a small slice of potential energy, this is basically just gearing us up to solve for gravitational potential energy. So we have gravitational potential energy. It's experiencing a force due to gravity. This force due to gravity does change as this object might get closer or farther away from the object. So let's input what we have. Yeah. So starting with this sort of first step, equal to minus this is just a way of saying, where is the force directed between objects of mass? So it's this is the force of gravity. This is Fg that I'm writing down. And this is the sort of position vector, or the tiny slice of it, dl. All of this just to get plus mg and some slice of height, or dy. I'll say, so for gravitational potential energy for U of G, so for gravitational potential energy, I'll say that's it's equal to the initial gravitational potential energy plus whatever height you have this object at, mgy, or just gravitational potential energy is mgh. Why did I take off this first term? Well, we'll say that's at the Earth's surface, since most of the problems we solve are, most of the experiments we do are on Earth's surface. We're going to say that's the potential at the surface is 0. So we're going to say that this is 0, and that just leads to gravitational potential energy. All right. Way too big. Notice when I have to write quicker, my handwriting gets bigger. Okay. For this example, we have a bottle that is on a shelf. This bottle is 0.35 kilograms, and it is 1.75 meters above the floor. Go like this. So what is the potential energy of the bottle when it's on the shelf? And what is the kinetic energy of the bottle just before impact on the ground? Let's do just a small picture. So we have a bottle on a shelf. That is some mass, and it is a certain height from the ground. We're going to say the ground down here is 0. So 0 height. That also means that if the bottle was on the ground, it would have 0 potential energy. So pretty easy to start out with. What is the potential energy of the bottle when it's sitting on the shelf before the fall? So just gravitational potential energy is mass times acceleration of gravity times whatever height it is. Yes, we have this. Height of this. And I forgot to put do it in order. Okay. I didn't do this beforehand. Let me. So we have just about 6.01 joules of energy. Finding just the potential energy when it is on the shelf. Okay. Find the kinetic energy of the bottle just before impact on the ground. So this is where I'm going to take this problem and make it a little conceptual. Let me put the picture right there. And This is the before. Let's do the after picture. So just the briefest moment before the bottle hits the ground. What height is it at? It's at a height of 0. Well, let's step back and examine the energy of the two types. So we want to know, in one part of the problem, we wanted to know potential energy. And in the second half of the problem, we wanted to know kinetic energy. So let's look at both of those in each of these two pictures. While the bottle is up here and on the shelf, so this is the initial potential energy. I'm just going to say it's a maximum. That's where it starts out. That's its full amount. When the bottle is falling, as it decreases its height, so looking in this equation, height value gets smaller and smaller and smaller and smaller. So the potential energy is going to shrink and shrink and shrink until final potential energy is 0. Okay. Now let's look at kinetic energy in the same exact way. So while the bottle is up on the shelf and it's perfectly still, it's not moving on the shelf. It's not moving. Remember what the equation for kinetic energy was? 1/2 mv squared. So since it's not moving, kinetic energy is 0 while it's up here on top of the shelf. But as the bottle falls, it decreases in height, but it speeds up. So this is just the property of falling objects. It speeds up as it gets as it keeps falling. So it's speeding up, speeding up, speeding up. So this velocity value is getting larger and larger and larger as it approaches the ground. And right as it reaches the ground, that is as fast as it's going to go before it has to stop, because the ground is going to stop it. So that will be the kinetic energy of the final position right here is a maximum. So we have this shift. Look at these two situations. We have maximum of potential up here, 0 kinetic. We have 0 potential and maximum kinetic down here. This is a we could assume. So let me finish this question by going, within the system, there is no loss of energy. Remember what we were saying earlier, that energy is neither created nor destroyed. So the energy is just transferred from one form into another. I'll say all of the potential energy is converted into kinetic energy. So in this case, I could just say potential energy, the change in kinetic energy. We saw that this is just mgh final kinetic energy minus initial kinetic energy. I've just shown up here that it was 0 when it's sitting on the shelf. So same sort of deal. We have kinetic energy final is the same equation that we've done above here, but kinetic energy equals it this time. 350 kilograms So I could have, right after this paragraph, just said that since it's all been transferred, it's all going to equal just this value. But if you want to do this math again, we have this sort of little proof for it. All right. You see, energy can freely transfer from one form into another. Okay, so that's potential energy. And we have just enough time for elastic potential energy. All right. Same exact setup as before with gravitational potential energy, except this time we're using Hooke's law. So it's just the same initial step that I've given. It's some arrangement of a force over some distance. In this specific case, we are putting in Hooke's law. For this force. And springs usually only bend, or springs only compress or stretch in one direction. That's why I'm just saying this for one direction. Putting in Hooke's law. Dx equals, that's just a positive kx dx. Actually showing the integral this time, we'll say that potential energy is kx dx. All of that will equal 1/2 kx squared plus some potential energy constant. It's whatever the potential energy is already in the spring. And this is the same thing I could say with the gravitational potential energy. If I am stretching a spring, compressing it, I'm putting in some potential energy. But if I leave it alone and just let it sit there, that's its initial state. That's this right here. So I'm going to say that while it is at rest, this term goes to 0. So it doesn't have any energy when it's in its equilibrium state. So we can just say the potential energy for a spring or elastic potential energy is 1/2 kx squared. Okay. Last little example for the day. We have a basketball player, does another slam dunk, and hangs on the rim just for a moment after he makes the shots. And we have this sort of system that is, this person is now elevated above Earth's surface, and they are sort of holding on to the rim that's sort of spring-like. We want to know how much potential energy is in this system. So just like drawing a big circle around this end of the basketball court. How much potential energy is in this system? The basketball player, 110 kilograms. First, let's start out by saying that total potential energy, I'll say total is equal to, whatever sort of change is happening with gravitational potential energy and elastic potential energy. So I just put this S, actually, yeah, so I put S, this could be an E if you'd prefer. I'm going to keep it as an S for spring. So we have this sort of change in potential energy. Let me write this out a bit more in full. The gravitational final minus the gravitational initial plus the elastic final minus the elastic initial. And for the initial case, so the problem sort of starts out with this person already has made the shot and is hanging there. We're going to say that the initial case was when this person was already on the ground, right before they sort of made this shot. So we'll say that, we'll say GI, so the initial potential energy. So initially, when player was on the ground, equals 0. Same sort of thing for the spring of the basketball hoop. Just say same sort of thing, equals 0. So that's a way of dealing with, finals and initials. Say the initial case was before this all happened. Let me shrink. Now we have potential energy is just its final positions. So it's final, gravitational potential energy, final elastic potential energy, which is just arranging these two together. We have mass, gravity. I'm going to say h for height. So height off of the ground. Why am I calling this h and not like y? It's because I'm going to use y for this next term. I'm going to say plus 1/2 k y squared. we'll say y is how much the basketball rim deflects downward. Okay, from here, it's a matter of just doing this large calculation. We're given basically all of the components of this, and we're just adding up the two separate forms of potential energy that are in the system. So there's potential energy just by being off of the ground, and then there's potential energy stored in the basketball rim. So let me do this. I should be putting a total over here equals let me zoom in so I can write clear. Newtons per kilogram. This is 0.50 meters. Don't need to zoom in that much. All of this plus 1/2 times, what did we have? We had kilonewtons for the spring constant. That's something to convert. Newtons per meter. And we have centimeters that we have to convert to meters. And this term right here is squared. We can't forget that. Finally, we have a total potential energy of 6.2 times 10 to the second joules. All right. So hopefully we've seen from today that we can transfer between two types of energy, kinetic and potential. We could go back and forth from one to the other. We can add up many different types of energy also. So say, in this problem, I could have also made something moving. And then I could say add up not the potential energy, add up all total energy. And that could be, a problem. I could arrange just from this example. So energy is neither created nor destroyed. It's merely just transferred from one thing to another. We'll continue with this tomorrow, and we'll definitely finish this by the end of the week. And I think the last thing is I'll send an announcement about this also. I finished out adding questions to the homework, so you should have enough to study this chapter 6 and 7 material for this upcoming exam next Tuesday. So I'll send an announcement about all that in a bit. Other than that, if you guys have questions, you could let me know. And if not, I'll see you later then.